Alright, so we'll begin with, or we'll try recalling what we had learned in the previous class. Do you guys remember what did we do in the last class? Slight test of the memory that you guys have about what we were doing so far before we broke for the new year. We had started dealing with complex numbers. That is where we talked about what are the different types of numbers, how do we deal with square root of a negative number kind of scenario. That is where the imaginary thing came into picture. And then we said, okay, complex number is nothing but a mix of real and imaginary element to it. And then we looked at different ways to add, subtract, multiply and divide complex numbers. And does that help you guys recall it? Am I saying something that I have not taught? Samriddhi, with me? Samriddhi is trying to recall.
Wait, can you repeat that? My speaker was.
Okay. Now I was saying that before we dispersed for the New Year break, we were learning complex numbers. That is where we talked about real and imaginary component of a number, which together is called a complex number. And what is the imaginary component? Then we looked at how do we add, subtract, multiply and divide complex numbers. We looked at some interesting concepts around it. And then we also looked at a situation where if I have to do x square minus y square, if I have to factorize it, I can say x plus y times x minus y. But if I have a situation like x square plus y square, I have to factorize it. That is where the complex number played an important role. We said, okay, fine, we can still convert. So when I have something square minus something square, then I can factorize it this way. But when I have a square of two things being added together and I have to factorize it, we try forcefully injecting a minus here, and then minus 1 times y square, and then since we know minus 1 is nothing but I square, so this became x square minus I square y square, and we were able to factorize a sum of two squares also. So this became x plus iy times x minus iy. These are the things that I remember based on what we have discussed so far. Yeah? Yeah? So, now we are going to extend our learning on the complex numbers further and look at some more interesting elements of it. So, a complex number can be represented in three different forms. One is called rectangular form, one is called polar form, and one is called the exponent form. So rectangular, polar and exponent form. And we'll look at all those different forms and try understanding what exactly it means and what is the difference between them and how we can move from, when we have a complex number in rectangular form, how do we convert to polar form or vice versa. And then we look at some more interesting concepts around it. Hey Vishal. Vishal, can you hear me okay?
Yeah.
Okay. The good news is that you have not missed anything, but I would suggest try joining on time so that unlike today, other days you might miss something. Okay. So I was just doing a recap of what we have done. So summary of that is we are dealing with complex number unit which is on complex numbers, and we have done some basic operations around that. We are going to the next, and also when we talked about complex numbers, we also learned how do we locate a complex number in a complex plane. Correct? So in today's class, we are going to learn different forms that we can use for representing a complex number. What is the correlation among them, and how do we convert a complex number in one form to another form or vice versa. And then we look at what do we mean by modulus and argument of a complex number. So these are some of the topics that we'll try covering. And then there are some more interesting elements to it where you multiply one complex number by another complex number or an imaginary number, and what happens visually, how do we relate to it. Okay, so let's get started. So as I mentioned, there are three different forms. One is called the rectangular form, other one is called polar form, and the third one is called exponent form. So these are essentially the three forms in which you can write any complex number. And just to help you guys refresh your memory, when we talk about a complex number, we are talking about a number like, let's say, complex number C1, which is equal to A plus BI or A plus IB, whatever makes sense to you guys. Where this is the real component and this is the imaginary component. So if I write this thing as is here, this is my rectangular form. The form that we have dealt with so far, that is called the rectangular form. Okay, so I'm not going to deliberate further on that one. I'm just reaffirming that this is the rectangular form, and then we'll come to polar form and exponent form in a little bit. Are you guys with me so far? Yeah, Samriddhi, Vishal, both of you as well. So now let's forget about polar form. Let's first try understanding what do we mean by magnitude and argument of a complex number. Have you guys got any familiarity with the terms that I'm using right now? What do we mean by magnitude of a complex number? If anybody wants to share, please go ahead. Now? Vishal? You have heard about the magnitude and argument of a complex number? Yes, Sahit, welcome.
I see.
Okay. So Sahit, we are continuing from where we had left. So we are talking about complex number. Complex number is a unit that we were doing before we dispersed for the New Year break. So we talked about what is a complex number, what is the real and imaginary component of it, how do you deal with adding, subtracting, multiplying and dividing complex numbers, how do we use complex number and how do we represent that in a complex plane. Those are the things that we had covered. Now we are talking about what are different forms of a complex number. There are essentially three forms: rectangular form, polar form and exponent form. And these are nothing different. They are just three different ways to represent a complex number. And again, a complex number is nothing but a number which has real component as well as imaginary component to it. So so what I told everybody here was, we are used to seeing a complex number like this, 3 plus 2i, where 3 is the real part and this is the imaginary part. And this together is called a complex number, which I am representing as a z right now. Yeah. So in the previous classes, we also talked about how do we plot or locate a complex number in a complex plane. And complex plane is nothing different from the coordinate plane that we are used to seeing. In the coordinate plane, the horizontal axis is called x-axis and the vertical axis is called y-axis. Here we don't call them x and y, we call them real axis and the imaginary axis. Okay. So if I am trying to locate this 3 plus 2i in this complex plane, so this is, let's say, 1, 2, 3, 4, 5, minus 1, minus 2 and goes on, 1, 2, 3, 4. Okay. So here when I am trying to represent this 3 plus 2i in this plane is called complex plane, where you have a real axis and an imaginary axis. If I am trying to locate this point 3 plus 2i in this complex plane, I will go 3 units along the real axis because my real component is 3. So 3 here and 2 units along the imaginary axis. So 1, 2 here. This works essentially the same way you deal with coordinate plane, just that the nomenclature and the way we think about it is a little different. That's it. But everything else was the same way. Is everybody with me so far? Sahid, everybody? Where are Sahid's buddies? Davik and Arus are missing. Arus anyway joins on Sunday morning. But Davik is missing. I believe he'll be late by 15 minutes. Okay. Anyway, so now we just recalled how do we locate a complex number in a complex plane. What do we mean by magnitude and argument of the complex number? It is simple. Magnitude of any complex number means the absolute distance between the origin and that complex number. Absolute distance between the origin of the complex plane and that point. If I have a complex number here, if I am talking about the magnitude of that, I am talking about this absolute distance without a plus or minus sign, absolute distance. Okay. So here, when you say this is my point 3 plus 2i, it means along the real axis the distance is 3 and along the imaginary axis the distance is 2. So here to here it is 3, here to here it is 2. And this is nothing but a right angle triangle that you can visualize. And when you're talking about the magnitude, you will find out this length using the Pythagorean theorem that you all know. So this distance, let's say, if I call r as the magnitude, which is a term used more often in this context. So your magnitude will be nothing but square root of this distance plus this distance. So 3 square plus 2 square, that's it. So this becomes square root of 9 plus 4, 13. And I did not put, see again when I am doing square root of 13, I will say my answer could be plus square root 13 or minus square root 13. We will not deal with sign here, primarily because when you are talking about magnitude of a complex number, you are talking about the absolute distance. It doesn't have to be complemented by a sign to it. So it will always be a positive value. Does it sound okay? Shahid? Okay. I'm assuming Shahid is able to follow me, okay? Because, yeah, okay. Now I keep reminding you guys to acknowledge what I'm saying, right? Because sometimes if I assume that everybody is understanding, regardless of how good or bad I'm teaching, I'm making a mistake, right? So, okay, anyways, so summary of that is, if I'm talking about the magnitude of a complex number, I'm essentially talking about the exact distance, the absolute distance between the origin of the complex plane and the point in the complex plane. So that is how you will use the Pythagorean theorem to find it out. Even if now, since you have seen it visually, so tomorrow, sorry, this absolute distance or magnitude was nothing but 3 square plus 2 square. And if you relate it with this, what you're seeing is, if you have a complex number, absolute distance or the magnitude of this will be nothing but square root of your real component plus square root of sum of square of real component and the imaginary component. Now look at it. See, this magnitude is nothing but the exact distance, the absolute, the distance from origin to this. Let's say you have a complex number z2 equals 5. That means you have a 0i. What will be the magnitude of this one? Nothing but r will be nothing but square root of this plus square of this, which is same as square root of 5 square, which is 5. So this kind of relates to it, right? So basically, if you try absorbing this as a concept, if you have an imaginary component, that is only adding angle to it, angle to your real this thing. Yeah, you're lifting it by a certain angle. That's how your I is getting added to it. If there was no I, you were talking about only the real part of the real component of any number that you can term as a complex number otherwise also. Am I making decent sense so far? Vishal, Samriti, okay. So this is the absolute distance from origin to that number in the complex plane is called the magnitude. What is the argument? This is the argument, angle phi or theta, whatever you call it. Basically, argument is nothing but the angle that this line joining origin and the complex number makes with the positive of the x-axis or the real axis. This is the argument. So now you can relate it, say okay fine. If somebody says okay find out you have a complex number this, find out the magnitude and the argument of this. You will say my magnitude is square of this plus square of this, add it together and then the square root, that is my magnitude, which is this distance. And what is the angle? Okay, so let's say if this is, let me not say phi, I will say theta. That's easy to pronounce. So here in this case, if I look at tan of theta, that will be what? This divided by this. So the imaginary component divided by the real component, 2 over 3. If I relate it with this, so this one we got as square root of 13. If I relate it with sine of theta, so sine of theta in this right angle triangle will be 2 divided by r, which is nothing but square root of 13. So this will be 2 over 30, square root of 13. If I am relating it with cos theta, cos of theta will be equal to adjacent side divided by the hypotenuse, which is nothing but 3 over square root of 13. Now you have to find out theta. So in this case, theta will be tan inverse or arc tan of 2 over 3. In this case, theta will be equal to arc sine of 2 over 3. Or if you are using this representation, your theta will be arc cos of 3 over 30, square root of 30. Net summary of this is magnitude of a complex number is the distance, the absolute distance from the origin to that complex number in the complex plane. And theta is the angle this complex number makes. I mean, when you join the complex number with the origin of the complex plane, theta is the angle that it makes with the positive of the real axis. That's it. So if you are talking about a complex number in the third quadrant of this complex plane, theta will be the angle, this angle here to here. And you can apply the unit circle concepts to even derive this. But are you guys okay with what we have discussed so far? Sahit, Vishal. So one line of takeaway, we just looked at how do we relate or find out the magnitude and the argument of a complex number. What exactly does it mean? So if I had a complex number z equals 6 plus 8i, my magnitude will be, if I call it as r, that will be square root of real component square plus square imaginary component square, which eventually turns out to be 36 plus 64 equals square root of 100, and that will be equal to 10. We got 10 as my magnitude. So when you try visualizing it, you'll say, okay, if I'm plotting this complex number in a complex plane, this 10 is nothing but the distance from the origin of the complex plane. Now, what we saw was, this is I, is a vertical component, the imaginary component of the right angle triangle that we were visualizing. Let me put it this way, 6 plus 8i, I'm talking about some point here, 6 plus 8i. So this 8 is the vertical distance and this one is the adjacent side, if I'm visualizing this as a right angle triangle. So my theta, if I don't want to do much of a calculation, I will assume this as a theta. So tan of theta would be equal to this by this, or imaginary component by the real component. Our theta will be tan inverse or arctan of 8 over 6. So just by having a complex number, you would be able to find out what is the magnitude and what is the argument of the complex number. So we saw this form is called the rectangular form of a complex number. Now we are going towards the polar form, and polar form is just another form to represent that using the magnitude and the argument. Meaning, if I had this, let me get rid of the numbers and use this. Use a complex number using variables. Let's say I have a complex number z1 equals a plus bi. So if I visualize that in the complex plane, this distance is a and this distance is b, and this point is a plus bi. And stop me guys if I'm going fast or if I'm not making sense, okay? Because many times I don't make much sense. So you guys have to be very honest to let me know that, sir, can you repeat, okay? So I have this complex number, I visualize that in the complex plane. This is my a and b. So, and if this is my theta, so if using this one, if somebody says find out the magnitude r, that will be nothing but square root of a square plus b square. And the theta or tan theta would be b over a. Let's use r for now, okay? So that we don't deal with complex looking equations here. Sine of theta would be, or I will say b will be equal to a tan theta. Similarly, if I say sine of theta, that will be b over r. This is my r, which is square root of this thing. So b over r, or I can say b equals r sine theta also. Okay. Now let's look at cos of theta. So cos of theta equals a over r. That means a will be equal to r of cos theta. If I get this value of a and b in terms of r, and so basically r is my magnitude and theta is my argument. If I am rewriting this whole equation using the magnitude and theta, I will replace a with this and I will replace b with this. So this way what happens is I can rewrite this equation as a, which is r cos theta, plus b or I times b is my r sine theta. Here r is common, I can write this as cos theta plus I sine theta. This is nothing but the polar form. So if you just do a recap of what we have talked so far, we just learned if I have a complex number, meaning a number with a real component and an imaginary component to it, magnitude of that is nothing but square root of the sum of squares of the real and imaginary component, and theta is the angle that it makes with the positive x-axis when you join the complex number with the origin of the complex plane. And from that, using the basic Pythagorean theorem and the basic SUKA-TOA rules that we are all aware of, we could rewrite or interpret this a and b, which is the real and imaginary components, in terms of the magnitude and the argument of the complex number. And we could rewrite this z1 equal to a plus bi in the form of z1 equals r times cos of theta plus I times sine of theta. This is nothing but called the polar form. Does it sound okay? So my confidence is 0 if I don't hear a confident yes from you guys. So you guys have to help me boost my confidence. How about Vishal and Sahib? Would you guys help me boost my confidence? When I say boost my confidence, I mean, am I making sense so far? Okay, so Samriddhi and Praneeth.
It's kind of confusing, but okay.
No, so don't see. I'm a very sticky teacher. I will not.
No, I understand it, but it confuses my brain. Like, it just confuses a little bit. Like,
So-
the letters,
Right.
you know.
Right. No, so again, the clue here is you have to visualize first. If you have a complex number, you have to visualize this like this first. Okay? That this is my real component, this is my imaginary component. Yeah? Once you have visualized that and drawn that on a piece of paper, then you can clearly see I have a right angle triangle here, where theta is my angle that this line makes against the real axis, a positive of real axis, and r is the magnitude, meaning the distance from center of the complex plane to that complex number. After that, whatever I am doing, I am just kind of relating them. Trust me, I mean, there is nothing complicated here, because if this is my right angle triangle, this has to be, this is my hypotenuse. Square of that will be square of this plus square of this. That's what Pythagoras has told us, right? So that is my magnitude. This distance is my magnitude, where a and b square of this plus square of this, square root will be by this length. Now what I am doing is I am applying my trig functions to relate a, b and r. And once we relate r in terms of a and b, and relate a and b in terms of r, basically using the same trig functions. I have done nothing fancy here, right? I have done what is tan theta, what is sin theta, what is cos theta. I have a, b and r, right? R is my magnitude. And from that, I am deriving a and b value just by flipping the things, right? I mean, I got sin theta equal to b by r, so that means b equals r times sin theta. I got cos theta equal to a by r, that means a equals r cos theta. So whatever I had from the original complex number, I am replacing my a and b value, my real and imaginary value, with the things that I have got here, because it helps us relate it with the magnitude and the argument of the complex number. Did I give you a right storyline, or I got you more confused or more worried? Vishal, Sahib? Yeah? Okay. So let me make it a little easy for you guys now. So in the beginning I said there are 3 ways or 3 forms in which you can write a complex number. So if I have a complex number z equals 4 plus 3i, my magnitude, first thing, as soon as you see a complex number, okay, what is my magnitude? What is the absolute length of this complex number? Nothing but r, which is square root of squares of these two, which is nothing but 5. Okay, you got your magnitude. Now I can rewrite this is my rectangular form. Now if I rewrite this in the polar form requires me to write this in the form of this. I will not use 4 and 3, I will not use a and b, I will use magnitude, which is r, times cos of theta plus I sin of theta. And cos theta and sin theta we can visualize using this as a, by visualizing this complex number in the complex plane. So this is the y component, y equivalent component, this is the x equivalent component. So y over x will be tan theta. This over this will be my sin theta. This over this will be my cos theta. So here r is 5. Cos theta will be again horizontal component over the hypotenuse. See, I'm not probably making much sense here because I'm thinking like a layman. I'm forgetting about all the premise of complex number and all those fancy terminology. I'm visualizing this like a right angle triangle. This 4 is my horizontal component, this is my vertical component, and this is my r. So cos of theta is horizontal component, which is a by r plus I times sine of theta. Sine theta is here, the opposite one, 4. The imaginary component, 4 over r, which is 5. So this is the rectangular form of a complex number. This is the polar form of a complex number. Does it sound okay? And there is a third form which is called exponent form, and that is a very interesting form because that will help you multiply complex numbers also later on in a much more easier way. But the only thing that the exponent form brings into life is this whole thing is represented in the exponent form as e to the power theta. I think this is called Euler's formula or something. I did not use it.
Euler's formula?
I'm sorry?
Euler's formula?
Euler's, I think you pronounce this as Euler's formula. This is a term I recall.
No, one where you like the power of pi something equals to 1.
Yeah. This is not 1. This whole thing that you have inside can be represented in this form. So I will do one thing. Euler's formula, I vaguely recall the name of that formula. So I will probably touch upon that when we meet again. Okay. Or I can cover that in the SAT class also. Any which way is okay. But what I'm trying to say here is this whole thing can be repainted in the exponential form by just replacing this whole thing by this. Nothing changes from a calculation standpoint, but this whole term that you have gets replaced with e to the power phi, e to the power theta. What is that you recall, Praneeth? Can you help all of us get on the same page? That's okay. I mean, when I was just going through the syllabus for today's class, right? I came across this term. I will probably now double click on this one and I'll explain that to you guys later on. So, what is the significance of that also? Correct? Just saying that this is called this probably would not go down well. But from today's objective point of view, I just wanted to make sure that we are all clear about the 3 different forms of a complex number, in which 3 different forms in which a complex number can be represented. One is called the rectangular form, second one is the polar form, and third is the exponential form. These 2 are exactly the same, just that one element of it gets represented in this way. Okay. Now, just to give you a glimpse of it, let's say tomorrow you have a z1 and z2 as 2 complex numbers. You represented them as r1 e to the power theta. Let's say both have same magnitude also. E to the power theta 1 and z to the power, the second complex number can be represented in the exponential form as r e to the power, or let's say it's r1 and this is r2, e to the power theta 2. What will happen is when you are multiplying these two complex numbers, which anyways we are going to double click on that in future classes. But when you multiply these two, you will look at this as a mathematical term and you'll say, okay, this is R1 times R2 times e to the power theta 1 plus theta 2. So multiplication of complex number becomes much more easier. I mean, you can obviously multiply it the regular way also, but I'm saying this just simplifies your whole calculation effort. Yeah? Alright. So we just got acquainted with the three different forms in which you can represent a complex number. And just to repeat, those are rectangular form, the polar form, and the exponent form. Polar form is nothing but when you convert a complex, when you derive the magnitude and the argument of a complex number, meaning argument as in the theta, the angle that it makes with the positive of the real axis, and the magnitude, the absolute distance between the origin and the complex number, and rewrite this in this form, that is polar form. So while I was explaining this to you guys, we just saw how do we convert a complex number from a rectangular form to a polar form. We just saw that. Unknowingly you learned that. We can look at some more problems to see if we are able to deal with it in a much more visual way. So Vishal, I know you were clear about the concept, but when you were trying to connect the dots, that is where sometimes you were feeling that I'm getting lost. So that can be taken care when we kind of practice few problems. That will get us closer to the concept and the application of it. So let's look at some problems. Okay. So we have a question that says, what is the modulus of -6? What is the modulus of -6 minus I? Don't round it. If necessary, express your answer as a radical. So sometimes you'll have the question, okay, this is the complex number, find out the value of -6 minus I. This is nothing but the same, the absolute value. That's what it's hinting at. Okay? So, would you guys be able to find out the modulus real quick? These are complex numbers, -6 minus I.
What's the question again?
I have a complex number -6 minus I. Okay? We are being asked to find out the modulus of the complex number or the absolute value.
Okay.
That should be an easy one. So let me keep you guys a little busy. So we have one complex number is this. Other complex number is -12 plus 5I. Please help me find out the modulus of both the numbers. Don't try rounding it. You can express that in the radical form. Meaning, if it comes to a place where you are left with a square root of something which you are not able to find out the perfect square, leave it in that form. It's okay. Help to solve these two problems before we jump onto something beyond that. Everybody got the question, right? Sahit, Vishal, Smriti, Puneet. Please let me know when you guys are ready.
I'm confused on the question.
So we are trying to find out the modulus, or the absolute value of these complex numbers. What is the absolute value of any complex number? Tell me. What do you remember? Yes, Samriddhi.
I got square root 37 for the first one.
Okay. How about the second one?
I'm still doing the second one.
Okay. Yes, Praneet.
For the first one, I got the same thing, square root 37. And then for the second one, I got 13.
Okay. So, fine. So Vishal, I mean, again, I know this is a concept that we just learned 10 minutes ago. So, obviously, sometimes it will take few minutes to digest it. So, basically, again, just to repeat it. If I'm talking about this complex number, I will visualize that in a complex plane minus 6 minus I. So, let's say this is 3, 6, 9. This is minus 3, minus 6, minus 9. 2, 4, 6, minus 2, minus 4. Okay, minus 6 minus I. So minus 6 is here, and I, that is minus 1I. So somewhere here. So I'm talking about this point. When I'm talking about the absolute value, I'm talking about the distance of this from the origin of the complex plane. And this will be nothing but, if you visualize this as a right angle triangle, this distance is 6 in absolute terms, not saying minus 6, and this distance is 1. So it will be 6 square. So this length is what we are trying to find out. This is the hypotenuse. So 6 square plus 1 square, the square root. That will be my modulus or absolute value. Does that sound okay? Vishal? Yeah. So for this one, again, when it comes to absolute value, see whether we are here or in this quadrant or this quadrant, what we are ignoring is the sign part of it. Because my absolute value is absolute distance. Meaning I need to know this distance and I need to know this distance and do a square root of sum of their squares. So that means whether it's a plus 6 or whether it's a minus 6, it doesn't really matter. Because we are just trying to find out this length. Length of this line is 7. I would not say minus 7. Correct? So that's why when we talk about magnitude, we kind of tend to ignore the quadrant. We just try to find out where exactly they are and find out the absolute length of these line segments. And we use that and apply that in a Pythagorean theorem to find out the absolute value. The absolute value or the magnitude of the complex number. Yeah. So in this case, it will be the absolute value of this. Magnitude of this will be 12 square plus 5 square root, which is nothing but a Pythagorean triplet. So 13. 12 square 144 plus 25 169, which is 13 square. So R equals 13. And if you have the same thing, you have to find, see, when you're trying to find out the magnitude, you don't care about the sign which quadrant they are in. But when you're talking about finding out the argument, let's say if I'm talking about this guy, then I have to find out the theta. And that is where you will say, okay, fine. How much angle it is making to get to this point. So argument actually helps you find the direction. and magnitude helps you find out the absolute value. Yeah. So, and when you come here, you'll apply your understanding of the unit circle. You'll say fine. You will find out this angle in absolute terms. How much is this angle? If I visualize this as a right angle triangle, this is 6, this is 1. How much is this angle? Which is this one? And you'll add pi to it. If I'm talking about this one, minus 12 plus 5i. So minus 12 will be somewhere here, 5 will be here. So you will find out this angle and subtract that from the pi. That will be your argument. Does it sound okay to everybody, or I'm kind of messing around?
Yeah, but I haven't watched the video again.
Yep, that's how I get more views. No, I'm just kidding. I have not started thinking more views yet. While I keep making, more, what do you call, shorts these days. I mean, every day when I go to bed, when I upload the video of the class, I make one short also and give a link to that one, so that more people start watching it, because when people watch, I get feedback, and that helps me fine tune some of the things. But yeah, again, more people, when I say more kids, that's what I mean here. So coming back to what we have done so far. So we talked about, we just did a recap of what is a complex number, how do we visualize a complex number in a complex plane, and what are the 3 different forms in which we can represent a complex number. So that is where we learned about the rectangular form, the polar form, and the exponential form. And then we also just saw one scenario where we converted one complex number from a rectangular form to a polar form. So we have just 10 more minutes. So what I want to do is, in next 10 minutes, I want you guys to deal with one problem. And again, trust me, while I kind of make the board dirty when I'm teaching you guys, and I keep bragging about saying that no, you have to get your hands dirty. Literally, it's very much important. So when let's say if I give you guys one complex number z1 equals 6 plus 3i. Let me 6 plus 3i. If I ask you to find out, let's do 3 things about it. Find out the magnitude, find out the argument, meaning the angle, and then rewrite this in the polar form. Let's see if you guys are able to do that real quick. I'm repeating myself. We have a complex number in the rectangular form. I want you guys to rewrite that in the polar form, and also find out the magnitude and the argument, which anyways you'll end up doing, because polar form is rewritten in the form of magnitude and argument only. So once you find out the magnitude and argument, you can just rewrite this equation in the polar form. Try giving it a shot. I'm giving you guys next 5 minutes to do it, and if you guys get stuck, don't worry about it. I will use the remaining 3-4 minutes for doing it myself in front of you guys. Okay? Is everybody clear about what we're trying to do? How part I will leave it for you guys to try. Struggle, deal with it, grapple with it, that's okay. We'll figure it out. So I'll be muted for next 4 minutes. Yes, side. What's happening with her? You're getting kicked out.
Sorry, I just disconnected.
Ah, okay, not a problem. So I have given one problem for everybody so that I can enjoy next 5 minutes of my time. I have given this complex number in the rectangular form, which is z1 equals 6 plus 3i, and I want you guys to rewrite that in the polar form. So give it a shot. I am hibernating right now for next 2 more minutes, and then I'll wake up. Okay. Anybody close to being done? Right, Samriddhi, Vishal, Sahit.
I'm still working on it.
Would you need 2 more minutes? Okay, let me give you 2 more minutes, okay? I don't want to discourage you guys from trying. In fact, I encourage. So, let's see. Okay, one more minute, okay? Because don't want to keep you guys hostage here for long enough, and I'm also a bit hungry after a little bit. Okay, so Samriddhi, tell me, how far could you go?
I was trying to do, but I'm really confused.
Okay, wipe off all the things from your mind. Look at this like a much younger version of yourself, meaning when you guys were much younger and much more fearless. That's how we look at it. Yes, Praneet.
My thoughts something.
Okay, tell me what is that?
The magnitude as square root 45,
Uh-huh.
then the angle was approximately 27 degrees
Okay.
after rounding, and then so I got square root 45 sine 27 plus I cos 27.
Okay. So let's look at it this way. So I'm not contesting whether your answer is right or wrong. I'm just trying to show you guys how I will solve this. This is my complex plane. My real component is 6. So let's say this is 3, 6, 9. So I'm talking about around 6 and 3i. Let's say this is 3, 6, 9. So I'm essentially talking about this point as my coordinate. I mean, this is the point that I can locate on the coordinate plane, which is 6 plus 3i. So what will be my angle? Angle will be, if this is theta and this is 3 and this whole thing is 6. So tan of theta is equal to 3 over 6. That is one thing I found. So theta will be tan inverse of 3 over 6. That is one. So 3 over 6, that is 0.5. Theta equals to tan inverse of 0.5. Now, I don't have a calculator right now with me, so I will lean on what Praneet said. So my theta comes, let's say, how much you got? 27 degrees, right, Praneet? Approximately?
Yeah, after rounding.
Yeah, okay, approximately 27 degrees, let's say. Okay. And what is my magnitude here? Magnitude is nothing but square root of real component squared plus imaginary component squared, which is 36 plus 9 square root of 45, which is 9 comma 5, which is 3 square root of 5. Square root of 5 will be 2.232 or something. So that will be 3 times square root of 5. 3 times 2 point something up, maybe 6 or maybe 7, approximately 7. I'm just making it up. So now if I have to rewrite this in the polar form, my polar form of this one is always r times cos of theta plus I sine of theta. My theta is 27 degree, r is somewhere around 7. I'll just plug it in, that's it. Does that sound okay? Samriddhi, Vishal, Sahit. Alright, so with that being said, I will let you guys go, enjoy the rest of your evening, and if there's something that is still not gone down well, the video is always there for you guys. Watch it once. When you're watching it, right, the best strategy is watch me do something, then pause it, and then you try repeating by yourself. Because This is the magical weapon. More you use it, more comfortable you will get with it. Okay. I mean, don't use a marker on a notebook, but yeah, a pen. When you do it more, you will see that it starts becoming much more easy for you. Okay. So with that being said, I will let you guys go. Enjoy the rest of the evening. Talk to you guys on the weekend. Alright? Bye bye. Bye Samriti. Bye Vishal. Bye Sahit. Bye bye. Bye bye.